You want to start the recording? All right. Assalamu alaikum, everyone. Thank you all for coming to this machine learning talk with Brother Younes Mourri. We're very excited to have him here, very proficient and accomplished in this field. And he'll be giving an introduction talk to machine learning as well as its applications, and then also leaving some time at the end for question and answer. So a quick bio about Younes. Younes was born and raised in Morocco. He currently teaches artificial intelligence on campus and online at Stanford University. He has worked on Coursera's #1 course, machine learning, and #1 specialization, deep learning. Younes co-created 3 artificial intelligence courses for graduate students at Stanford. He also teaches the natural language processing specialization on Coursera. Younes received his bachelor's degree in mathematics and computer science, as well as his master's degree in statistics, both from Stanford University. And alhamdulillah, we're super excited to have him here. So with that being said, I'll go and give it over to him. So thank you all.
Yeah. Thanks, Yusuf, for the introduction. And thanks, everyone, for having me here. I mean, before we get started, if you feel comfortable and in a position to turn on your camera, please feel free to do so. Otherwise, don't worry about it. But yeah, so today's goal, I prepared something small for you to just give you a little overview of machine learning and deep learning and what's out there. But really, the point here is for me to do whatever I think or whatever you think is more useful for you. So I'll get started and start presenting what I have, and feel free to stop me as I'm going. And I'll also try to keep a few minutes at the end to just give like at least some career advice of things I have seen that work and things that I've seen that did not work, as I think that might be a little bit useful. So let me share my screen. And before I get started, how many of you have already taken a machine learning course? Perfect, just one. Okay. All right, so I'll assume most people did not take. Okay, perfect. Okay, so yeah, and I think there's a question. Someone raised their hand. Feel free to unmute yourself.
Well, I think that person might have been raising their hand as in they've taken the machine learning class.
Oh, got it. Okay, sorry about that. Okay, perfect. So let me share my screen. So everyone should be able to see. Everyone can see my computer. Perfect. All right. So I'm just going to talk a little bit about some various topics in machine learning, and also try to give you an overview of machine learning and of what's going on out there, some deep learning models, and show you just basic training algorithms and how they work. So over here we have a learning process in machine and deep learning, and usually the process is the same. So whatever you're usually looking at or trying to build, usually you have some type of input, and then given the input, you have some model in the middle, and then you have an output, right? So in this case, we're going to find f such that f of image is equal to 1 if it's a cat, and 0 otherwise. And this could be face verification, this could be any type. It could be like signature, identity, any type of model. Wait, let me.
Younes, I think they're asking if you're comfortable sharing the slides after.
Oh.
Well, we are recording the event for all the participants here, so inshallah, it would also be on our YouTube channel. So you'll be able to watch everything again, inshallah, when it's live on our YouTube.
Perfect. Yeah, thanks. So yeah, basically the models are all similar in the case, at least in supervised learning. So before I get started, there's supervised and there's unsupervised learning. Supervised learning is usually where most of the money is actually in supervised learning. For example, is someone going to click or not? And this is just an example. Is it a cat or a dog? Is it a human or a non-human? But most of the industry applications are in supervised learning. and they all follow the similar template. So you have an input, you feed it into your model, and then you get an output. So what does a model consist of? A model usually consists of an architecture plus some parameters. So an architecture could tell you, how deep your model is, how large your neural network is, how small it is, how shallow it is, So that's the architecture of the model. And then the parameters are those weights that are actually being used inside your model. So the parameters usually are learned, and they're learned through a process called gradient descent. So over here, you have a loss after you compute your output. You have a loss that tells you, relatively how well is your prediction. For example, if you are predicting, whether the input is a cat or not, you might get a probability at the end between 0 and 1. So usually if the probability is greater than half, you'd classify it to be a cat. Otherwise, you'll classify it to be not a cat. So given this loss, you're going to use that loss to at least gauge where you are. And you're going to update your model by computing the gradients. And the gradients are, you can think of them as some type of information that's going to allow you to update your parameters or your weights that you are using when making the prediction. And please feel free to stop me as I'm going. So you're going to keep doing this, you keep, making the prediction, getting the loss, updating the weights, using those weights again to make the prediction. And weights could be, for example, how many of you are familiar with weights when I say weights? Okay, perfect. So let's say, for example, you're trying to predict the price of a house. You have like 3 rooms, and then you have the size of the house, and then you have the number of bathrooms. So you're going to multiply, okay, so each room might cost, $50,000. Each bathroom is going to cost me $20,000. And then each square foot is going to cost me, I don't know, $5,000. So then you're going to multiply, the 50,000 times the 3 rooms plus the 20,000 times the number of bathrooms plus the price of that the square foot times the number of square feet that you have. So the price of like 50,000 and the 20,000, like these prices, you can think of them as weights that you multiply with by the actual feature. When the feature in this case is the number of bedrooms, the size of the house, and so forth. Does that make sense for everyone? Okay, so when I say parameters, these parameters are actually those weights that I'm telling you: the price per house, the price per bathroom, the price per square feet or per square foot. So you need to learn what these parameters are. You need to learn what these weights are. In this case, we have the input, which is pixels. And say it could be 64 pixels by 64 pixels if it's black and white. You would basically need to know like how much is each pixel worth, So when you multiply the pixels by the actual parameters, that's going to give you the output. Everything is clear so far, right? Perfect. So things that can change when building these models. And I'm not going to get into too much detail of how you compute the gradients and so forth, but I just want to give you like a quick overview. So you have the input, you have the output. That's going to change. For every input, you might have a different output. The architecture can change. And the architecture is the depth and the width of your model. The loss can also change, right? So the different types of problems will have different types of loss functions. For example, if you're doing a classification problem, you're trying to solve whether the input is a cat or a dog, you might want to use some type of log loss, and this is just a different loss function. If you're using predicting the price of a house, then you might want to use a mean squared loss. For example, the prediction minus the actual price squared. And then you can, divide by the number of predictions you had. So that's like an overview of things that can change. Now, what else could change? The activation functions can change. For example, basically, what are activation functions? Activation functions are you can think of them as other functions that are inside your neural network. For example, you know, if your numbers inside the neural network are getting larger and larger, you might want to put a threshold and cap at that threshold, you know, or if they're getting smaller and smaller, you want to put a threshold and cap at 0. So to remove all the negative numbers. The optimizer is basically how you compute these gradients that allow you to update those parameters. Those will change. And then other hyperparameters you can think of these hyperparameters at the rate at what you're learning, you know. For example, how fast you want to learn these parameters. So that's, for example, hyperparameter. So, okay, so far so good. Any questions about what I said so far? Just a quick overview.
And real quick, I'll just say I don't have a question, but if people do have questions, go ahead and either put them in the chat, or Younes, are you okay with them raising their hand or just unmuting and talking?
Yeah, they can just unmute for sure.
Okay, perfect. So yeah, you can use the chat function or feel free to unmute and ask any questions, inshallah.
Okay, perfect. All right, so let's look at this. Once we use an image, the first thing we want to do, at least when computing, so logistic regression as a neural network. So how many of you ever heard of logistic regression? Okay, perfect. So logistic regression is a type of regression method that allows you to predict yes or no, you know, given the image, is it a cat or not a cat? And it usually outputs a probability between 0 and 1. So if it's greater than 0.5, you would classify it to be a cat or not, right? And when you have a logistic regression, you basically have some type of weight, as I said when I described the housing price problem, like the price of each room times the number of rooms, the price of each bathroom times the number of bathrooms, and so forth. So that's price of each bathroom, and so forth, could be encoded as the W matrix over here. So you can see W. So that's basically the parameter you're learning, right? And then the X is the actual features. So it's the number of bedrooms, the number of square feet, the number of bathrooms, and so forth, in the example of a housing price. But in this case, we're using actually an image, right? So what does this mean? W, for each pixel, we need to learn the feature. That's going to be multiplied by our original input X, right? And then you add the bias term, you can ignore the bias term, the plus B. So that's going to give you a huge number, you know, as you have, I don't know, 255, I don't know, vector of size, and the size doesn't matter, but as you have a very large vector and you multiply each pixel, because originally the image is like, say, 64 by 64. So you have to unroll it to one vector, right? So that's your xi. And then as you multiply each pixel by a certain number, you're going to get a number that's definitely not between 0 and 1. Does that make sense? Why the number is not between 0 and 1? Because the number of pixels could vary, and the price per pixel is also going to vary depending on how it's learned. And I'm not going to talk about how it's actually learned, but I just want to give you like an overview of what's going on. So then we feed it into a sigmoid function. How many of you are familiar with the sigmoid function? Perfect. So a sigmoid function is a function that takes in, say, a number and maps it between 0 and 1. So in this case, this W transpose times X plus B is being fed into a sigmoid and is going to give you a probability between 0 and 1. Okay. Now, based off that probability, then you're going to decide whether the image is going to be a cat or not. Does that make sense for everyone? So the question is, now what's the hardest part here? Who wants to take a random guess? So let's say the sigmoid function is some function maps input to output, right?
I think somebody asked if the W is the hardest part.
Exactly.
The
The W is the hardest part. So the W is the hardest part. So that's the point of machine learning and deep learning and of gradient descent, of all these optimizations that go on. Once you have an input, the hardest thing is you have to learn what the W is, because if you have the W, the rest is pretty much straightforward. You're just gonna plug in the results of W transpose X inside your sigmoid function is gonna get you the probability. So to learn the W, that's what we were doing over here. So, you know, you have an input, you get a loss, which tells you how far you are from the actual target. And then you keep using those gradients to update the W or to update the parameters. And then you have all these things that are can change. Does this make sense so far? And an activation function, so the sigmoid I just spoke about, could be an example of an activation function. Other activation functions that might be useful, who wants to take a random guess? So in this case, we're predicting yes or no. But there could be other cases. So let's say you have, let me think, you have more than just cats. You have cats, dogs, and elephants, right? And you given a picture, you want to predict whether it's a cat, a dog, or an elephant. Now you can't predict just a probability between 0 and 1. Right?
Would you then need to like set values for the individual species or something, and then have the function map to that?
Exactly. Yep. So basically, in that case, you want to output, you know, a vector of probabilities. Say the index 0 corresponds to cats, index 1 corresponds to dogs, and index 2 corresponds to elephants. Then you're going to output a probability, and then the highest probability is like whatever the index is will correspond to that actual input. So that's a different type of activation function called the softmax. So you see in this case, we used what can change is the activation functions. You know, the other things that will change are also optimizers. Like how do you learn these parameters? So that's like what machine learning and AI is mainly about. Is how do you learn these parameters? At least the supervised parts, which takes in labeled data like inputs and outputs. So okay, does this make sense? This is just a very basic logistic regression as a neural network, thinking of logistic regression as, you know, taking an input and predicting yes or no. Perfect. And what's happening here is these xi's over here, each xi is being multiplied by its respective w. So you can think of the arrows as the w's. And that's why when you see a neural network, you have these edges, like edges connected, nodes connected with edges. I don't know how many of you already saw those. But basically, you can think of each edge as a W, as a parameter you're trying to learn. Okay, we can continue now. Over here, multi-class. So this is what I was talking about, where you are trying to predict several classes. Maybe in this case, class 1 is you know, dogs, class 2 is cats, and class 3 is elephants, you know. And in which case you have 12% that it's a dog, 73% that it's a cat, and 4% that it's an elephant, you know. And then you have several weights that are being multiplied by the corresponding xi's, and then you have a different different type of activation for multi-class. Does this make sense? So in multi-class, there are different approaches. You know, one approach is if you just want to use the sigmoid function that predicts between 0 and 1. What you can do, you can actually do what's called the one versus all method also, where you like you set a label to 1, so for example cats, and 0 to dogs and elephants. So it's 1 versus everything else, you know. And then you're going to see what the prediction for that is going to be. Then you're going to set 1 to dogs, and then 0 to the elephants and the cats. And then you're going to see what the prediction of that's going to be. And then you're going to do the same thing to the last one. And then you're going to classify to be the score with the highest prediction. So this is like, usually this would take like, 30 or 40 minutes in actual lecture to go through and step by step. But I just wanted to give you like a quick overview of how things work over there. All right, so multi-class. Now what we're going to add a hidden layer inside the neural network. So previously we just had our inputs, we multiplied it by our W, we feed it into some type of function, we got a prediction, right? So now we're going to add a hidden layer. How many of you are familiar with hidden layers? Perfect. So the way you can think of a hidden layer is, let's go back to the housing price, predicting the price of a house, right? So when you're predicting the price of a house, let's say that you have, as inputs, the number of bedrooms, the number of square feet, the number of bathrooms, right? And then let's say you're going to use that to predict the school quality in that district, right? And then you're going to use the school quality to predict the price of a house. So what these hidden layers are doing, they're trying to learn actually different features other than the features you just gave them, And then you're going to have another W that's going to be multiplied by the hidden layer. So just to recap, imagine the housing pricing problem that I gave you in the beginning. You have the bedrooms, you have the square feet, and you have the number of bathrooms. You're going to use those to find different features such as a school quality in that area, security in that area, commutes or restaurants around that area. And then you're going to use these new features, multiply them by a new W to predict the actual price.
We have one question in the chat, Younes.
Yeah.
Lena asked,
for it.
Do you verify the correctness of a hidden layer?
That's a good question. So the hidden layer usually, it's very hard to verify. In face detection, I have an image over here. Let me show you. Yeah. Sorry. Yep. So in face detection, if you were to actually print what these hidden layers are, you can actually see that each hidden layer is trying to figure out the eye, then the eyebrows, then the nose, then the mouth. So basically, that's one way to at least see that, try to print and understand what's going on in your model. But usually these hidden layers, you can think of it as a black box. But in this case, you can see that layer 1 has barely like slight edges that are being detected. Layer 2, these edges starts making a little bit more sense. Like there's a nose, there's an eye, a little bit. You can see layer 2, and then layer 3, it starts making a little bit even more sense. So does that answer your question?
Yes, it does. Thank you.
Perfect. Okay, so over here you can see we're adding a hidden layer. And then we're going to use the hidden layer again. You can think of each arrow as a W that you learn. And to learn the W, it's a little bit more complicated. But there are packages that allow you to learn what the W's are.
Younes, I was just reminding them that they can just unmute to ask questions.
Oh, perfect. Yeah. So over here, we saw that's how we went from one image to like adding an extra hidden layer to getting an output layer. So the hidden layer you can think of as learning different features, which will then be passed on to your next W matrix. And then you can get your output layer, and then you can do whatever you want with the output layer. You can make it a probability that goes between 0 and 1. You can turn it into like a vector that is has a sequence of probabilities for each class. So there's a lot you can do with these hidden layers, and then with the final output layer also. So this is the encoding. So this is what I was talking a little bit about. As you print each hidden layer, you can see things becoming more fully formed, and your model becomes more useful. Basically, it starts understanding more things as the neural network gets deeper and deeper. But of course, you cannot, like, how do you decide the number of hidden layers? It's something that you will experiment with. Do you want to go 10 hidden layers? You want to go 3 hidden layers? How many nodes in each layer over here? In this case, we have 3 in the hidden layer. Do you want 4? Do you want 10? These are things usually that come a little bit with more practice, more experience. But no one has like a defined set of rules that will help you determine the number of hidden layers. One thing that works better is the deeper the network, the better it is. Just general, the more it could capture more. Basically, the deeper the network is, the more complexities it can actually capture. All right, so
I have a question.
Yes.
How do you know that one layer has worked on specific features? Like layer 1 is working on one specific feature and layer 2 is working on another. So can there be any duplicate layers that work on the same features again?
Yes, this is a very good question. So usually what ends up happening is the earlier layers tend to work on more specific type of features.
Mm-hmm.
For example, in this case, just trying to capture the edges, trying to capture the boundaries.
Mm-hmm.
And then as you progress through the layers, you are trying to learn more abstract concepts until you finally try to recognize what a face is. But this is just an intuition. Usually it's a black box. In this case, like what's happened here, you're actually printing the hidden layers.
Mm-hmm.
But in reality, it's very hard to know what each layer is doing. So that's why if you're to look at the history of for example, machine translation, when you use Google, initially it's made use of statistical machine translation. For example, you would use, the first models were just if-else statements, some type of regular expressions, and it will give you like a slight small translation that's not very good. The next one made use of statistical machine translation, and meaning that you made use of a lot of probabilities what the next sequence might look like given the current inputs. But like with the latest advances in machine learning and deep learning, you end up using end-to-end models, meaning you just feed in the inputs, you get the outputs, and you think of it as a black box. You learn the weights through certain techniques called gradient descent and optimization, and then it'll give you the results automatically.
Okay.
Perfect. Thanks for the question. Okay. So this technique is called encoding, meaning what's happening, you're basically encoding information in the hidden layers. So let's see how you can build a concrete application. So there are several possibilities that we can look at, but let's start with classifying whether it's day or night. And then maybe we can look at face recognition. Art generation is, how many of you have seen paintings generated by AI models? Yeah, perfect. So that's art generation. It uses neural style transfer, which is also another technique, another model that you can learn. And then keyword spotting is like, when you say, hey Siri. Oh, sorry, I turned this on. I didn't mean to do that. Perfect. So yeah, basically it spotted the 2 keywords I just said, right? So that's keyword spotting, which is another thing you can use with machine learning and deep learning. Other things are like image segmentation. I don't know if you saw, but I think last week Tesla, or at least I saw a post done by Tesla where they're going completely vision-based. no longer using those sensors. So these are like a few things, but basically for each deep learning approach that you use, you need to choose an architecture, meaning, you know, the width of your neural network, the depth of your neural network, how shallow it is, you know, do you start with 10 hidden layers, then you go to 3, then you go to 5, do you go 10, 10, 10, do you go 3, 3, 3, you know, and then you want to choose a loss depending what type of classification you want to be using, and then a training strategy, how to learn these weights. So given an image, let's classify taken during the day as 0, or during the night as 1, right? So our end label is going to be 0 if it's taken during the day, 1 if it's taken during the night. So the first thing, we need data. So let's say we have 10,000 images that you randomly took. And then you want to obviously create a split. And I'll talk about that in a bit. But for now, let's say that you have the following image. And then you want to see what the resolution is going to be, right? But let's see what our output looks like. Y equals 0 for during the day, y equals 1 for during the night. So what's the last activation going to be? In this case, going to be a sigmoid function, right? Because as I said, the sigmoid function gives you a probability between 0 and 1. And don't worry if you don't understand what I just said. Anyway, just the overview, the main takeaway is you basically have an image. You have y equals 0 or y equals 1 for day or night. And then we're going to use a sigmoid function as the last activation. And then what architecture are we going to use? We're going to use a shallow neural network, right? Because this is not too much of a complicated task. All right, so we're going to use a log loss. So, you know, how many of you are familiar with loss functions? Okay, so here's an example of a loss function. So what we said, our y is either 0 or 1, right? Our actual y. So let's say, and what is y hat? Y hat is bounded between what two numbers? The prediction. If we're answering yes or no.
Is it just between 0 and 1?
Yep, exactly, between 0 and 1. So let's say that in this case, y equals 1. So which part of the loss function are we looking at? The first part or the second part? The if y equals 1. If y equals 1, what happens to the second part?
Turns to 0.
It goes to 0, right? So you're only looking at the first part. So, and we said y hat is bounded between 0 and 1. So if you predict 1 for y hat and y equals 1, then you get 1 times log of 1. And log of 1 is 0, right? So you get a cost of 0, a loss of 0, which is perfect. Ideally, you want to minimize this loss, right? Let's look at the other scenario. Let's say y equals 0. Then you are looking at the second part, right? Because the first part is going to go to 0. So you're going to end up having 1 times, and let's say your prediction y hat is 0. So it's 0 and you predicted 0, very close to 0. Then you're going to get 1 times log of 1 minus 0, which is also 0. Does this make sense why this loss function works? Because let's say y is 1, but you predict something close to 0. Then you're only looking at the first part, right? Because y equals 1. So you get 1 times log. And let's say you predict something close to 0. Now, the closer you get to 0, log of something as close to 0 as possible could hit to infinity. Because the function is like this, right? So the closer you are to 0, the higher the loss is. At least in the first parts, because you have 1 times log of your prediction. So that makes sense, right? You can see how this loss works. Ideally, you want to minimize it. Now, from basic calculus, how do you minimize a function? You take the
Taking
derivative, set it,
derivatives.
yeah, go ahead.
Yeah, we take derivatives and bring that to 0.
Perfect, yeah. And you try to solve for that parameter.
Hmm.
Now, in machine learning and deep learning, sometimes it's hard to do that. So if you're to do it for linear regression, you're going to get a closed form solution known as the normal equations. But in this case, what we usually do, we use gradient descent. That's going to at least help us converge to the minimal solution. So that's what gradient descent does. It's basically you're taking the derivative with respect to certain parameters, and then you keep updating those parameters to reach the solution, or at least as close as possible to a solution to get your W's that will help you minimize this loss. Does that overview make sense? Perfect. All right, so I mean, we still have a few minutes. I'll also keep a few minutes at the end for questions and answers, and then also if everyone is interested, maybe I can. Everyone here is almost a student, right? Most people are in college.
Yeah, most of the people in this Zoom room right now are current
Perfect.
students.
Yeah, and then maybe I can also give some advice on internships and on how to get a good job as an AI engineer, as a machine learning engineer, if everyone wants. I think that'll be very useful. But let's look at this last example before we can go ahead and talk about that. So let's say you want to build a face verification, for validating students' IDs, So you have a picture of every student labeled with their name. So you have an input, which is a picture, and the resolution. So usually pictures are of width by height by 3. And the reason why it's by 3, because you want RGB values. So each layer will tell you what those values are going to be. So in this case, it's 412 by 412 by 3. And then the output is whether it's the actual person or 0 if it's not. Now, there is an issue with this type of model, because let's say, at a school at Stanford or at Berkeley, you have, tens of thousands of students, right? You're going to build a model with tens of thousands, to give you a probability over 10,000. That's going to be very difficult, right? So how can you do it? Here's a simple solution. You compute the distance pixel per pixel. And if it is less than the threshold, then y equals 1. So you can just do some type of Euclidean distance between corresponding pixels. That will work if the face is actually centered, the background is the same. That might work, but it's going to be hard. Here are a few issues. You have background lighting. That's gonna hurt. You have, what if someone's working, wearing makeup, or if they have a beard, or if they had a haircut, or so that's also not gonna work. The other thing is, what if the ID is outdated? Like he has an old picture or she has an old picture. That's also not gonna work. So here's what we can do. You can basically encode the two pictures. Let's say you have the actual person in the database who he claims to be. So you get the actual vector for that person, and then the picture of the person trying to verify. And then you use a deep network to compute the two vectors. And then you can compute the distance between those two vectors using Euclidean distance or some type of cosine similarity function. And then that's going to tell you whether the threshold works or not. Does this make sense, this technique? Better than just going 10,000 students predicting which one is the highest probability. You go and you actually use the actual encoding of that student. And that's how basically face verification works. Okay, any questions so far? So I'm just trying to give you an overview of machine learning, of deep learning, of cool techniques that are out there.
Actually, Younes, I have a question, and it's kind of relevant to where we're at. Is this the same type of technology? I'm not sure if you're familiar, they were using in the Stanford dining halls. I think they were doing some facial verification. To,
Yes,
let people
probably.
in.
It's
Yeah.
the basic structure is actually the same. One of the best ways to use this type of technology is called Siamese networks, where you're actually training using shared parameters across two sister networks. So if you can think of one network, the other network, and then they converge at the end. So it is actually a similar technology. Of course, the architectures are slightly more complicated over there since it's actually being deployed, but it's the exact same thing. So now you know how these face verification systems work. And I'm sure like in TSA pre-check, they might have something similar. You can also use it for signatures. It's banks. If you have 10 million signatures, you cannot train a model. It's going to predict which class it belongs to out of 10 million classes. But given the actual signature and the current signature, you can use or build a similarity function. So normally in classification, there are two types. Either you want to learn the difference between two objects, and that's what you're learning, what is that difference, or you try to actually classify what's going on. So in this case, we're just trying to learn, what's this difference going to be between, an anchor and the current example.
Okay, yeah. So there was a question in the chat. Mohammed asks, how are some face ID recognitions not fooled by photos?
I mean, there's an entire branch in AI that tries to like fool image face verifications. You can actually fool it by photos, but there are other new technologies that allow you to even capture depth. So that's one thing. Maybe using some type of sensors to know, the 3D landscape of the person. But yeah, it's a good question. Thanks. All right, so I just want to go quickly. And so yeah, basically here's how it works. I'm not going to go into the loss function, how the loss function works, but usually puts an anchor, which is like the original picture. And then you have a positive image and then a negative image, right? And then what ends up happening, you're trying to minimize the distance between the anchor and the positive image. And you want to maximize the distance between the anchor and the negative image. Does that make sense? That's how the training works. So you have like an anchor and a positive image and then a lot of negative images. And you try to just make sure that when comparing the anchor and the positive image, you minimize that distance. And on the other hand, you maximize the distance between the anchor and the negatives. Again, model, architecture, parameters, and you keep doing the same thing, just as I mentioned previously. Other things you can do is use k-nearest neighbors. Say you transform it into a vector, you find the closest vector of all the other images. So that's just finding what are the k, like 5 nearest neighbors, and then maybe use one of those, Other things is you can use face clustering to group pictures of the same people. Like that makes use of another algorithm known as k-means clustering. Okay, so let's look at neural style transfer. So basically, neural style transfer makes use of content image and the style image, and it generates like the image over here, as you can see. I'll not talk about the technical details of neural style transfer, but just to show you some technologies out there that could be used to generate cool images. Anyways, this is the architecture. This is Did you hear them?
No, Younes, I think you might need to share your audio as well.
Oh, okay, it's okay. So basically, what's happened here, each blurb, this tells you like giraffe, tiger, elephant, lion, and it asks you to detect the word lion. So this is also like keyword spotting. But anyways, just for the sake of time, this is how the architecture works. Basically, you have like some type of window that goes by, and then you can use the window to detect whether it looks like more like lion or like giraffe or like elephant. Okay, so any questions so far?
I don't think there's any questions. Lena had a comment in the chat. She said, I've always been creeped out by Apple Photos grouping. Yeah, which is always.
Yeah. It's there's a lot to be done. So grouping is usually a different type of learning called unsupervised learning. And unsupervised learning is like, when you search something, a query online, they give you a bunch of relative, content out there like links. So that makes use of unsupervised learning. And then like k-nearest neighbors, k-means clustering, you're clustering articles together and recommending them to users on search. Other things to keep in mind is server-based versus on-device deployment. So once you have these model architectures and learned parameters, you can either like send it to the server, compute, and then send back and tell you what the result is, or you can use the on-device, have it on device. Obviously, if it's on device, it might take more space. So
Younes, real quick, there was another question Lena had about back with the sound recognition. She asked, are you using noise level or frequency in the case of detecting lion?
normally you transfer the noise into like frequency levels, usually, but most of the time of the latest speech recognition systems use transformer models, and it's usually end-to-end. So you just transform your data and then feed it in. It gives you the final outputs. So obviously, yeah, that's for the question. One last thing I'd like to talk about is server-based versus on-device. Obviously, on-device you have faster predictions, but on the other hand, it takes more space. And server-based, the app is lightweight, but it could take more time to get the predictions. There's image segmentation. And I'm just trying to, basically you can do a lot of cool things with, I think I stopped sharing my screen, right? Perfect.
Yeah.
So yeah, that was just an overview presentation. I hope that was helpful. I mean, I can talk now about like any questions you have, or I can talk if you're interested in some career advice. I can try to help with that. Just let me know.
Yeah, so thank you so much, Younes. And again, we have some time now. Participants or anyone in the audience, feel free to either unmute or use the chat. And if you have any questions, and then, I think Younes will also in a bit give some advice on sort of career path. But right now, if anyone has any questions, please feel free. And sorry, one other thing, if you want to private message the question to either me or Younes or someone else on the team, that works as well. But you're totally free if you're able to unmute. Oh, Younes, it looks like there's a question now.
Oh, perfect. So the question, thanks Hassan for asking the question. If you were to start learning ML, what advice would you give for going about that? I would say, it depends. Like, what are you? Where in undergrad are you? Are you like a freshman, sophomore, junior? Junior, perfect. So yeah, I would recommend at least like taking the intro to AI programming courses and the programming courses that are available in college. And then once you exhaust those courses, then internships is a good way to go about it, like trying to get a machine learning or deep learning internship. Other ways to go about it is to try to join a lab. Joining a lab, I wouldn't recommend joining a lab before taking the AI courses available, because if you join and you didn't take a lot of courses, a lot of the times they're going to make you like label data and do like busy, dirty work that you wouldn't want to be doing. But if you join in, like knowing how to deploy, I don't know, AWS instances and training your models, GPUs and TPUs, and knowing how vision works and how NLP works, and having a good, strong base and foundation, then it could be much cooler for you to join. Does that answer the question? Perfect. Oh, another question is which parts of Morocco I'm from. I'm actually from Tangier, so the north. And nice to meet you. Yeah, so any other question? I can talk a little bit about general advice that you can apply to machine learning or to deep learning. Your opinion, thanks Ahmed for the question. What's your opinion on using machine learning for stocks trading? I think it's a lucrative business. A lot of people do make a lot of money using AI and NLP and all these technologies for stocks trading. If that's what you're interested in, then go for it. But yeah, I think there are also lots of other impact areas that machine learning could be very useful, like in healthcare or in education. But yeah, people also use it for stocks trading. So they're also known as quants, if you heard of them. Many of them also use AI and NLP models. It's like, to get sentiments of stocks and of companies and how they're doing in the past. Like you can analyze tens of thousands of companies in a fraction of a second.
I have a question real quick,
yeah.
I guess, about quants. Would you need also like, I guess that business side knowledge as well as like the machine learning and the computer science to get into that? Or would you be able to handle it with just one or the other?
So quants usually are very technical. They are very, very good at computer science and very, very good at math. And they also know, many of them code in C, because especially if you go into high frequency trading, you want very low level type of programming language to optimize for speed. But usually quants are very, very math focused. They build models, and of course they might have some type of intuition, but usually most of the work is actually building models that figure out, sentiments of stocks, finding named entities of CEOs and founders and following them. And, I remember there was an incident, I think there was some type of spam saying like, something crashed, or I think president died or something happened, like White House incident. And then like billions of dollars were automatically wiped out from Wall Street, just because the models were automatically, identifying the stocks and trading. So yeah.
Well, I have a question actually. Assalamu alaikum.
Yeah.
Yeah, thanks for the presentation, Younes. I'm actually not a student. I'm a data scientist, about a year and a half out of college. But I wanted to get your opinion on what you think about, I guess, breaking into the industry and like still staying in the industry. I feel that from my personal experience that there are more hurdles to get into data science and machine learning in a full-time position as opposed to, say, software engineering. And I've noticed that a lot of the prominent people in this field will either have a PhD from like a high-level university if they want to work on a high-caliber team in a big company, or they are coming from a high-level university like Stanford, for example. So I don't know like what you think if things are changing or over time. I've just noticed, like, I personally live on the East Coast, so the scene is not as big as it is on the West Coast. But I've just like noticed that opportunities are a bit limited. Oh, also, there's this other Stanford lecturer named Chip Yoon, and she was saying that machine learning engineers and data scientists are more of a luxury kind of employees. So it's like if a company already has everything set, then they might hire a data scientist or a machine learning engineer.
Yeah, very good. Yeah, very good feedback there. Definitely. I agree with you. It could be really hard, but one thing that industry people are getting better and better at is they could identify people who actually know what they're doing and who actually did really good projects in the past. So in which case, what I would recommend for people who are trying to break into data science or AI industry is to have a very strong portfolio. And, you know, many things that students usually do, they go and they take, you know, I'm the president of this club and the founder of this club, and I did this and I did this project and I did that project. And, you know, like, you're not going to fool someone interviewing you by trying to, you know, have as many numbers of different projects as possible. Like, people usually try to look at, you know, when hiring, try to think of it as like a T-shaped individual where you know a little bit of everything, but let's say you go into one specific field and you are really, really, really good at it. Like, you have contributed to open source over there, you have deployed existing models, you have done like a serious research projects on that. And then that's going to make it much easier for you to break into the industry versus trying to be like a generalist where you go into the interview. Because if you're hiring someone, just think about it this way. Let's say you're building some type of app and you're hiring, you're building the face verification system. You don't want to hire someone who knows a little bit of AI, but you'd rather hire someone who's actually an expert in computer vision, who's been doing it for 3 years and who has actual expertise in computer vision. You know, that's going to make the entrance to the industry much easier. So my advice for people trying to break into industry or to data science, and you know, it could be like specific type of data science, like applied to real estate or applied, and then you can target those companies, and it'll be easier for you to break into those type of companies if you have an extensive portfolio. Contributing to open source is also very, very good, especially if your code is actually being used. So that's a big one. And also just meaningful projects usually help a lot. So if you worked on a project that's actually meaningful and that people are using, that's helped others, it's much easier to talk about during the interview, and you're more likely, you know, to be remembered by the person interviewing you. So yeah, I would say, like, you know, contributing to open source and focusing on actual meaningful projects are probably the two best ways of getting the desired job you want in data science or in machine learning. And this advice goes like for in general, because you know, your degree can only hold you up for like 2 or 3 months after you graduate. But the moment you graduate, 2-3 months in, it's no longer like your degree is good, but it's actually what you just worked on. You know, you cannot, you know, go to a good university and you know, keep using that for the rest of your life, being like, oh, I attended here, because you know, 2 years out, what really matters is what you actually contributed. So that's at least like my take on it. And yeah, hope that helps. And I agree with you. I mean, data science and machine learning and deep learning, it could be seen as a luxury, but it's becoming more and more critical.
Thank you so much. Yeah, I appreciate the advice. It's very, very helpful. Thank you.
Yeah. Of course, thanks. You know, Jakob. Lena. Yeah. I mean, yeah, 2 to 3. I mean, maybe that's an exaggeration, but definitely like 6 months in. Well, the point is that, you know, it really matters what you work on than what your resume says. Like, your resume could say a lot of good things, especially like people here in the Bay Area, they can decorate their resume really well. and you're going to talk to them, at least on paper, you're going to think that these are amazing people, amazing candidates. The moment you start working with them, you're going to realize that they lack a lot of experience. So yeah. Any other questions? No?
Younes, if there's not, if maybe you want to wrap up with just sort of that final like career advice. I know you already touched on that a bit in the previous answer, but
yeah, definitely. I can wrap up with final thoughts and final.
Also, sorry, Younes, to cut you off real quick. Would you also be interested in maybe dropping like your email or something in the chat if people want to reach out to you with more questions? Is that something you?
Yeah, for sure.
Here,
I'll drop it right now.
Okay, awesome. Thank you. So yeah, anyone who's here, feel free to reach back out to Younes. And if there are any other questions, please feel free. You know, there's still some time. You can answer. Otherwise, Younes will wrap up with some last bit of advice.
Yeah. So yeah, just thanks. I just sent my email. So just some final thoughts. You know, if you're in college, I would recommend, you know, and if you actually want to get into AI and machine learning and deep learning, I'd recommend trying to build, you know, relationships with professors, trying to get to know at least like slightly older classmates, because they're probably gonna go into industry before you. They might help you lead the way. They might lead the way for you as you're applying for jobs. The most important thing I would say is just, you know, working on, you know, meaningful projects, building good relationships with your classmates and with professors, joining a research lab if you can, and trying to focus more on the T-shaped individual rather than the generalists. Because, you know, as a generalist, like, you know, getting into a good university, it's good to be a generalist. Like, you want to show them that you were part of several clubs and that you did so many things and that you have a good, you know, extracurricular activities going on. And that's a great recipe for getting into these top universities like Berkeley and Stanford and so forth. But, you know, once you graduate from college, what's really matters, and, you know, even if you want to do a startup or a company or even get into a PhD program, having that edge where you are like really good at one specific thing is going to help you a lot in the long run. So my advice would maybe like you're going to start with machine learning or deep learning, but then maybe you're going to focus on natural language processing, you know, and then you're going to become really good at natural language processing, or you're going to become really good at computer vision, or you're going to become really good at probabilistic models. And with that, then like even if you go like you want to apply to a PhD program or to industry, once you're going to apply for that job and you're going to get interviewed, then you have something that's actually, you know, that puts you way above most other candidates. So I would say like focus on not being a generalist and at least having some type of edge. So that's one major advice. Another major advice is, you know, just make sure you're meeting friends and having fun and enjoying your college education. And, you know, you can be strategic about it. You can build up an edge in a certain vertical and also have time to go and meet friends and hang out and play sports and do everything you want. But just make sure you focus on, you know, not wasting a lot of time doing a lot of things that keeps you like in a shallow position. Try to build up that edge vertical. And yeah, meaningful work is always very important. Like, I'm sure a lot of you here could go and become software engineers and data scientists and work on ads or other things, but I think it's much nicer to go ahead and, you know, work on more meaningful projects. So, and this my takeaway. Well, I mean, yeah, that's basically, yeah, my few thoughts on this. But yeah, always remember to enjoy your college, your time in college. It goes by really fast. And yeah, if there's anything I can do to help people here, please reach out to me. I sent you my Stanford email. If you have any questions, I'm more happy to respond to them via email or right now. But yeah, thanks a lot for hosting me, and I'll stick around for another minute or two if anyone has any questions.
All right. Yeah, thank you so much, Younes. We really appreciate it. I hope the audience appreciated it and enjoyed it as well. Yeah, as Younes said, he can stick around for a couple minutes. Everyone also has his email. So yeah, thank you everyone for coming. Everyone's totally free to go, but if you have any other questions, you can feel free to stick around and ask.
Perfect.
And